Okay, in our last video, we saw some interesting things about um, the pressure in a liquid and a gas. And we would just recall that a liquid cannot be compressed very much. And that's an important, okay, I mean a tiny bit that's almost immeasurable, but for practical purposes, it's not enough to matter. So it can't be compressed. And so because of that, that means something very important. It means that if you have a liquid inside an object, okay, now a liquid can be under pressure. Be very careful you don't mistake the words under pressure and being compressed. So being compressed means that you can't squeeze the molecules together very much more than they already are. But you can have a liquid under pressure. Okay, so if you imagine that there's a liquid inside this in this box, let's do a little. There's my liquid in the box, and the liquid is under pressure. Okay, the sides of the box have been sort of pushed in, and there's pressure applied. Let's put that as a little arrows here from the box. The box is pushing in. Maybe these walls are closing in or something. Now, of course, they won't go very far. You won't be able to squeeze these walls in very far because the liquid cannot be compressed. But if you push on the liquid with the walls, the liquid will push back, won't it? Newton's law, Newton's third law. Every action has an opposite and equal reaction. And so that's what we mean by the pressure, right? The liquid is under pressure. So there's still a balance of forces, but there are definitely forces involved. And what's important is that the liquid will push back in all directions equally. Everywhere in the liquid will experience the same amount of pressure. So that's an important point. A liquid under pressure will, that pressure will be everywhere in the liquid, and it will push in all directions. Okay, so once we know that now, we can start to make a little device that could actually do something useful to us. Remember, way back, when we talked about energy and work, and we talked about something like an inclined plane. Let me just refresh your memory here. And what we said was that if you wanted to lift an object straight up in the air, you would have to apply a force equal to its weight, right? Which was maybe a lot of force. But we found that if you pushed it up a ramp like this, you could actually push with less force. But of course, the end result was changing what we call the gravitational energy, E. The energy is the way we account. It's the accounting system of the universe. So when you take an object and you move it up to here, you've changed its energy. How you change its energy, though, is a little bit variable. You have some options there. And so what we noticed is that if you lift straight up, like we did here, then the force is simply the weight, mg. But lifting up or pushing up the ramp, like this, somehow made it different. But there was an important thing that we noticed. If we imagine a ramp that has virtually no friction, or as little friction as possible, we notice that both things achieve the same result. They change the gravitational energy, or the position of this block. So the energy is the same in both cases. And that means if the energy change is the same, remember that the change in your energy is equal to the work done. That means that both of these mean we've done the same work. Remember, if we have a nearly frictionless ramp. We know also that if you add friction, you actually do a little more work on the ramp, but even that is still beneficial because work is force times distance. And so what happens is, if the energy change is the same going up by lifting or by going up the ramp, then what we have is the lifting force and the lifting distance has to be the same as the ramp force and the ramp distance. The product of those has to be the same. But you can manipulate. With the lifting, we used a bigger lifting force and a smaller distance. But you get the same result if you use a bigger, oh, sorry, I did that backwards, a smaller ramp force, right? Yeah, a smaller ramp force and a bigger distance. So the proportion still comes out the same, right? It's kind of like, you know, if you have 3 times 2, which is 6, and that equals 6 times 1. Well, if you take this number and you make it bigger, let's say you double it, 3 times 4, well then in order to make that the same, you would either have to double one of the other numbers, or you would have to change this proportion in the same way, right? You would have to double the 2 here, or the 1 here, and make it 6 times 2 to keep everything going. You have to do sort of the same thing, right? But if I raise one of the numbers up a certain amount, I can also achieve the same by switching the others. So if I make the 3 bigger and the 2 smaller, so let's say I triple the 3. If I triple the 3, watch what happens here. I make it 3 times bigger, then I have to still get 6, right? 3 times 2 is 6. So forget about this one. I'm looking at the first one. If I make this a 6, then in order to keep it as multiplying to 6, I have to reduce the 1. See, the force got bigger, the distance got smaller. And the same over here. So that idea of proportion is very useful. And so force times distance, you can play with that, and you can actually gain. So what we gain here is we're willing to push further up the ramp. See how much farther this is with less force, because humans can't generate enough force maybe to lift it straight up. So it's a trade-off. Well, that's going to come back now again when we look at fluids. When we look at fluids in an enclosed space, we can actually find a similar advantage. So I'm going to draw a picture for you here. Here's a picture. So I'm going to have a tank, and I'm going to go like this over here, and we'll have this littler. This has to be smaller, okay? And then what we'll do is we'll put some what we call little pistons, little things that seal up. Actually, I'm gonna redo that a little bit lower. Sorry, maybe down here. Put it down here. So what this is it's a piston, and we'll just color it all in. So this there, and over here we'll put a small one up here near the top. Okay, and then we're going to fill this with fluid. So let me get my crayon here. We're going to fill this up with liquid. It could be water, could be any kind of fluid. It doesn't really matter. But we'll do blue. We can use water. You can build this at home using little syringes, right? If you think about how a syringe works, these look like syringes, and some tubing. You could make this. Okay, now, here's what's going to happen. What we're going to do is we're going to examine what's going on at each of these places. So let's just say, for instance, that we start with the little small one. And what would happen if we pushed on this? If we applied a force down? There's my force. I'm going to give these numbers. Okay, I'm going to call this piston 1 and piston 2. So we'll call this force 2, the force on piston number 2. Well, if I push that down, it's going to squeeze the water. But the water can't be compressed. So the water now will be under pressure. But because it can't be compressed, the pressure is going to be transmitted in every direction against the sides of the tube, all over the place. There's going to be pressure now, and this water is going to be pushing everywhere in all directions against the wall. Now, as long as the tube is strong enough, nothing will happen. But it's also going to be pushing here up against this piston, this big one. And so what that's going to do is it's going to apply a force. That pressure is going to push on the piston and cause it to move upwards. So the force applied on that, we'll call it F1 for now, because the water can't squish. Now, if we used air, what would happen is the air would compress, and as you push down piston 2, the air would just squeeze closer together, and not much would happen on the other side until you really pressurize the air. So there'd be a lot more sort of like, I guess, play in the system. But this is pretty much going to be a trade-off 1 for 1, or it's going to be basically whatever happens at 2 is going to immediately make something happen at 1 because of the fact that the liquid can't be compressed, but it can be pressurized. Okay, so now let's look at the pressures. So there's a pressure created here, but we just said that that pressure has to be the same all through the liquid, which means over here, the pressure here must be the same. So the pressure at position 2 caused by pushing down has to be the same as the pressure pushing up right here. Pressure is the same in the liquid. So let's write a mathematical statement about that. Let's say that pressure 1 equals pressure 2. All right, now what does that mean? Well, remember, pressure is force per unit area. Okay, so this is force 2 and area 2. Now, what do we mean by area? Well, we mean the surface area of the pistons, the area that the water is pushing on. So we have to kind of imagine what these pistons look like if you were looking up at them from the bottom. So here's the bottom of one, and here's the bottom of the other. Notice how the bigger one has a bigger area. Area 1 is bigger than area 2. Now, what does that mean? Well, if we remember, the pressure has to be the same. And you remember what I was talking about with mathematical things. Let's look carefully at these two fractions. If area 1, if they have to be equal to each other, okay, so I'm going to put in red here. These have to stay the same. But it's very hard if they aren't, if they're the same, it would be easy if the areas were equal, right? Then the tops could be equal and the bottoms can be equal. But what if this area is bigger? Because see, over here, area 1, bigger. Well, what a bigger number on the bottom of a fraction does is it makes the whole thing seem smaller. Right? It makes the whole thing get smaller, which is that weird inverse relationship. So what this is trying to do is it's trying to make this fraction on the left side smaller. So that means that in order to keep it the same, to sort of compensate, this top number is going to have to get bigger. If the bottom, right? So that the fraction stays the same. If the bottom gets bigger, the top has to get bigger to keep it the same. And then if we think over here, here we have a smaller area, smaller. Well, if you make this smaller, it makes the whole fraction want to get bigger. So to keep the proportion the same, this force has to get smaller. So in order to keep these the same, we could write it like this without numbers. We could say, in order to keep them the same, because the bottom one has a very big area and the other one has a very small area, in order to make them the same proportions, F1 would have to get bigger and F2 would have to be smaller in order for everything to sort of stay the same. A big number divided by another big number can give you the same result as a small number divided by a small number. So what does that actually mean? Well, it means that we can use a very small force on piston 2 right here and push downwards on piston 2 with a very small force, but it will generate a very large force that pushes up on piston 1, right? I just noticed that I have a 2 here, and it should be a 1. I hope that didn't throw anybody off, 1 and 2 for the pressure. The force is much larger on the larger piston. So it's almost like we're getting an advantage. We're using a small force to push a little piston, and we're getting a big force on a large piston. So it feels like we're getting an advantage, and we are getting an advantage, but nothing is free, okay? Because now let's consider the energy change. Let me use a different color, maybe purple. Let's consider what's happening with the energy. Well, the energy is the work. The change in energy of this piston is how much work is done when you push it downwards. So that is the work, which is the force times the distance. And the energy must not change from piston 1 to piston 2. We cannot gain energy out of magic, right? Energy is conserved, we say. So what this means is if piston 2 is using a very small force, so let's put the work here, it's using a small force, but I'm getting a big force over here for this work. This is also force times distance. If I'm getting a big force here, once again, to keep them equal, this is going to have to be a very small distance, and this is going to have to be a very large distance when I multiply them, so that the two amounts here are the same. If you increase one, you have to decrease the other to keep it the same, which means this piston will move very far. But this piston might only move a couple of inches, or it might only move this far, d. So there is a trade-off. I'm losing something, just like with the ramp, the inclined plane. If you want to use less force, you have to use more distance. But that's okay, because distance is something that we can easily generate. It doesn't matter. We push a little longer, but we push with a small force. And this is the principle behind hydraulic and even pneumatic mechanisms that are being used to do work for us. You can imagine, okay, a very simplified system. You could build yourself a very simple lift. So again, what's happening here is you have the same picture. Okay, and I won't draw the whole water and all of that, but basically, here's your piston. So here you put some kind of weight. Maybe you probably couldn't lift a car with something as simple as this, but maybe something fairly heavy. So we'll put a big rock on here. And this rock is too heavy for you to lift because you cannot apply enough force. So you put your little piston over here, and you use your hydraulic fluid. You fill it all up with hydraulic fluid, right? Okay. And when you push on the small piston, you can now push with a small force that's easy for you to push downward, which creates a pressure, which transmits through the entire fluid, which creates a larger force over here because the area is larger. If the pressure is the same, the force in the area have to maintain their same proportionality. If the bottom area goes up, the force must go up. So you've generated a larger force here. And that allows you to lift the rock. As this moves upwards, it will lift the rock, right? Now, the problem is, or the trade-off is, that in order to do this, you're going to have to push this piston down very far in order to get your rock just to move up a little wee bit. The distance is much smaller. So you have to be willing to push with that small force for a long distance in order to make this trade-off work. But it doesn't matter because the force times the distance, which is the energy change, is the same in both cases. And so that's what we're going to be doing when we start talking about hydraulic systems. All right. Now you can imagine a system where, you know, you push a small piston like this one, and you do have a car up here. If you go to the car, or to the garage, sorry, and they have to get under your car, they put it on the lift. And they press a small button that activates a small piston that pushes on fluid inside the tubes, those big silver metal things that you see underneath that are on the lift. And when they push on the small piston, the lift goes up. But to get the car to lift up, you know, several, maybe 3 or 4 feet, they have to actually push the small piston much, much further. Now, of course, the system is much more complicated than that because it requires all kinds of sort of ways to release the pressure. How do you bring the car back down? And we're going to get into that. We're going to see how complicated hydraulic and pneumatic systems can work to create an actual car lift or something similar. But this is the basic principle or idea behind it. Generating large force from a small force by using or utilizing the fact that pressure must be constant and the fact that the energy has to be the same, the work done. And so a large force over a small distance or a small force over a big distance. And that is basically what we're going to be talking about in our next set of videos.